All right. So my name is Carlos Malzahn. I'm UC Santa Cruz. I'd like to introduce Jeff Lefevre, the first speaker today, who's going to speak about Skyhook. So his research interests are in cloud databases and storage systems, and he's currently leading the Skyhook project, which is programmable storage for databases. And it's part of the Center for Research on Open Source Software in UC Santa Cruz. And so he received his PhD in June 2014 from UC Santa Cruz database group and subsequently joined Hewlett-Packard Big Data R&D Vertica database, where he worked on integrating Vertica with external analytics engines such as distributed R and Apache Spark. So at UC Santa Cruz, his advisor was Neoclis Polizotis, and his PhD thesis title is Physical Design Tuning Methods for Emerging Systems Architectures. And there he introduces a new physical design methods for databases in the cloud. Specifically, he addresses relational database management systems, Hadoop, and hybrid multi-store, combined relational databases, and Hadoop co-processing system architectures. With that, Jeff, please go ahead.
Okay, great. So thanks for the introduction, Carlos. So I'll get right into it here. So overview, talk briefly and what Skyhook means in this context particularly is that we want to leverage the scalability and reliability of storage layers. So these are the storage layer properties that we can allow the database to benefit from. And how we're going to do this is we're going to return the data semantics as we stored inside the storage layer. And the goal of that is to really enable us to do some management tasks inside storage directly under the database. And that includes some offloading of work into the storage layer. And overall, the result there is we'd like to be able to scale the storage, right? As normal, this would scale the data I/O, but we also want to be able to scale the processing capability when we do that. And that embedded semantics is what's going to help us do that. Additionally, we address here database relational data management tasks, in the query processing or indexing. But there's no reason that we can't expose the same capabilities to other libraries. And that's something that we're looking at, of course, in this context with root files. We're also looking at it in the context of HDF5 files that interestingly have a virtual object layer that allows us to pass through operations down through the file API and map it back onto itself. So that property is kind of a key feature that we're looking into for HDF5 and how we exploit that in this root context as well. We can talk about that more a little bit later. So what is programmable storage? Here it's, like I said, this is pushing down some data management tasks into the storage layer. And interestingly, not only is it the typical task, but we can think of things like even resharding. So we might want to transform data or reshard it, in fact, under the storage layer outside of the purview of the database, and the database gets a lot of these benefits, and it's kind of blissfully unaware of what we're doing underneath, if we do it correctly, of course. So Skyhook uses Ceph. We extend Ceph object storage with our customizable functions. And that was developed here at UCSC. And the general programmability website is there for other programmability tasks. And this is Skyhook, which is specifically addressing databases. So for those who may not know much about Ceph, I think most people probably do, but the properties here is it's distributed, it's fault tolerant, it's widely available, and it's an object store. So while there's other API wrappers on top for different interfaces, the core entity is an object. So these are the entities that Ceph manages and maintains reliably. Here we're just going to focus on this direct interaction with objects library. And the interesting part about this that really is what we exploit in this Skyhook approach is with this library you can create user-defined object classes. So you can define a class with the methods, but essentially you can think of it as you can override the read and write methods with your own functionality. And that's kind of how we built Skyhook on top of this capability. Okay, so how does data storage look like in Ceph cluster? For those who aren't familiar, just a quick overview is the file is partitioned, and the partitions are, in this case, one-to-one with objects, in our case anyways. This is kind of the normal case as well. When the data is then stored in Ceph, it uses a placement algorithm that's pseudo-random based, so you get some nice balanced distribution of these objects, which is a hash on their object name or object ID. And that kind of distributes them across the cluster. And underneath there, you can see that there might be multiple storage servers. They each will store a collection of objects based on whatever the placement algorithm decided to give them. And each storage server has its own memory and CPU resources. So some of the properties here that I just want to point out that are important is that, to us, in this case, is that it uses primary copy replication. Writes are atomic and they're transactional. And most crucially, maybe, is that given an object name, your client can calculate where it sits. So it can figure out which server to ask for the data from. It also lets us do partial reads and writes of objects, so we don't have to read and write an entire object. We can update and place and this kind of thing. And nicely, of course, when servers fail, it redistributes objects across the available servers, which is identical to adding and removing servers for scalability, if you like. So then you might ask, well, why objects and not files? So in this case, we have a really high amount of flexibility. So they don't have to be uniform size. We can align these object boundaries along semantic data boundaries, which is kind of what we need for processing tasks. And we can even dynamically subdivide it or merge these objects back, so based on the current size or maybe desired size or maybe desired number of objects. So you're thinking it's similar to file chunking, except, or a stripe unit, for instance, but it's kind of hard to process a raw byte range of a stripe unit this way. So this is sort of the reasoning for why we do it in this manner. So how does it help us? It's all of the usual benefits of the storage systems. These custom classes that we're going to talk about lets us do this remote processing. And then, interestingly, we can also have metadata that we can store on a server. And it's actually queryable because we can store it inside the server's embedded key value store, which is a RocksDB. So we can storage servers can locally index data and metadata. We can both content data and also metadata, and we can query it at runtime locally. So these are all local operations to the storage server. So that's what we focus on. So if we bring back the SEP cluster, we have the objects distributed as we saw before, and then there's a little RocksDB, as I mentioned, and then there's where we store our indexes on each server. So if you think about it, the little red circles indicate where the processing is happening locally. And in each case, it's a local index lookup to every RocksDB and a local object read or write in the case of read or write. And this is what is able to exploit the local CPU and memory of those storage servers. So this is sort of invisible to the application layer at this point. It's all happening under the storage layer. So as you scale out these number of storage servers, because we're utilizing those remote resources, you're getting more CPU and memory and processing capability. So what's some other tasks you might think of? One common example we used is maybe you want to store or generate a thumbnail. So maybe when you write the original data, you would generate a thumbnail as well, and you can store that in the object or in this RocksDB. And then at read time, you could either read the thumbnail out, or you could read the entire object and generate a thumbnail on the fly. So if you write some code that does the generate thumbnail process, you can invoke that during the read or the write phase. And of course, the goal there is you'd reduce the data transferred, and you save the work by offloading that task of thumbnail generation from your client application. You've offloaded it right into the storage system, and at that point, it's a local op at that server. So there's plenty of other examples. We could do checksums. You can think of filtering and things. You can also think of compression or decompression. Those are possible as well. And it's really, as far as whatever you can write in a C++ class. In this example, you can see there's a C++ interface, and there's a Lua interface. And basically, the signature is there's an input buffer, and there's an output buffer. So on the left in the C++ example, if you want to compute the MD5, you basically unpack the input buffer, you read the data, you append it to the output buffer, and then you return. So that's sort of how you override, think of the read or write capability, or read or write methods in SEP, the standard read or write methods. And to note again in red, these are the functions that are executed by the storage server. So this is actually locally executed in place. And of course, then if you compute the MD5 and you send that back, you've saved all this network traffic because you're not sending back the entire object bomb, as well as the time to compute the MD5. So once we put all those features together, those capabilities, what we've done is we're going to do data partitioning with the storage. We're going to do remote processing with the storage, and we're going to do remote indexing with the storage. How this looks like is you can imagine a database, in this case Postgres, which is a single node database, that can leverage these Skyhook plugins in Ceph and allows us to sort of scale the single node database capability out more broadly across all of the storage servers. So you get a much broader capabilities in terms of I/O and CPU. And Postgres, like most databases, will have an external data connector or external data interface or external table interface or whatever they call it. In this case, they call it a form data wrapper. And these are the connections that basically connects the database to an external source. And in that source is where we can do the work and translate some of the query plans. For partitioning, what we do is we take a table data. On the left there, we have we partition it by rows, so we can do hashing. In fact, we do a jump consistent hash. But you can use any partitioning, range partition if you like. And then we're going to format the data. And for the data format, we have a flat buffer metadata description of the data. So the data is actually a flat buffer data struct. And in there, that's where we retain the data semantics. And basically, that's the table schema, so we know the data types and such. The object names are generated, so because clients can look them up, all you have to know is the object name that you want. So if you want to look up the whole table, you can just generate, if they're regular, all of the object names for the table. So there's no extra lookup mechanism to figure out what object we need. And here we're going to store partitions one-to-one in objects. And then, crucially, at the bottom we mentioned we don't have to keep track of the location. We just need to know the names of the table and the objects. So here's some of the capabilities we have. So the partition data, you can see the little red circle again. This is where it's local because that's an object. So any processing would happen object local on that remote server. So we can do selects, which is a row-based operation. We can do project, which is a column-based operation. And then we can also do some things like aggregations. So keep in mind this is aggregate on a single partition, so it's like a partial aggregate. But still you can compute the min of, say, every partition or the sum and max. You can also do sorting, or your other set operations if you like. And then if you wanted to do a global aggregation, you would need to do those again at the higher layer once more time on all of the sorted data or on all of the mins returned from every partition. You just compute the min of those. So you're still offloading and saving a lot of work as well as network traffic by doing those remotely. Next, briefly touching on indexing, so same table data. So the index that is created, we can create it on a subset of the columns if you like, you know, 1 column, 2 column, etc. We can also compute statistics on those columns, and they're stored locally. That's in progress actually. And we can do maybe more interesting things in this case. We can do splits, so you might want to sub-split a partition if it's too large for some reason, or you'd like to process it in partial of each where the partition itself is sub-partitioned. Then we can also do things like reformat. So we're looking at what does it mean when we translate a partition from row format into column-based format, or data format A, which in our case is these flat buffers, which is just a data structure, into data format B, which is maybe arrow, which is another data structure, which is a column-oriented format. So those are the kind of more complicated transformations we can do within storage, given these capabilities of the C++ and Lua extensions. And then so briefly, what does this all look like and how does it work? So we have developed some custom classes. So consider these 3 queries. Select from table T where there's a predicate and maybe project a couple columns from table T, or compute a small aggregate on table T with a predicate. And so these red circles are the functions that are going to happen in the storage. So those are what we actually push down and do. And we'll show some quick results here. And then we'll try to move on. Get back on track. So a data set here, we have a billion row table. It's a TPCH table, a standard table. It's about 140 gigs. And we partition that into 10,000 objects. So this is a fixed number of objects. So we have essentially 10,000 partitions. And on each partition, we're going to create a local index. So that's a remote operation, and it happens in parallel on all the storage servers. So that's we do create the local index on a particular column for the query. And then we'll look at a point and a range query as we scale the storage system from 1 node of storage up to 16 nodes of storage. And at the top end, in the client node, you can think of a database node, we just have 1 machine up there. And we'll compare if we do it the standard way, which is to return all the data to the client, let the client database do all the work, versus the Skyhook approach, which is push all the predicates that we circled in red down into the storage and just return the data that passes these predicates. So for a point query, this is a single row out of the billion. We're going to look for a particular value of these 2 columns. So the y-axis represents execution time, and the x-axis shows as we scale out the number of storage servers. So, as you might imagine, if we do I/O scale out, the blue represents we're scaling out the I/O, so you get the parallel I/O from the storage, but the client side is doing all of the work. So, of course, you get the parallelism of I/O, but the red bar then shows Skyhook approach, which is where we push down some of that work, which are those red circles I showed you. So as you scale out the storage, you not only get the blue I/O benefits, but you get the offloading benefit as well. And then furthermore, if you think about keeping the metadata or statistics, in the orange case there, we use an index on these particular columns. So now what we've done is we've issued an index lookup query to every one of the 10,000 objects, and it checks its local index, and it either returns nothing, or it finds that actual matching row and returns just the row. So that's the only data coming back in the index case. And in the red case also, it's also the only data coming back, except the red case, it's actually scanning the data live. In the index case, it's just doing a lookup and finding the row directly and sending it back. So unsurprisingly, we could get my scale out with a story. And then another example is a point query. If you think of a range query, and we look at different selectivities here, we can apply filters. On the left-hand side, it just simply shows an integer filter. So this is an integer-based range filter. And the red and blue bars show the same kind of trend. On the right-hand side, we might do a little bit more complicated filter in terms of maybe CPU impact or resources required, like a regular expression search. And you can see the red and orange bars show basically the same trend here, modulo level 2. So the question then becomes, what other processing could you do? Regular expression. We talked about generating, thumbnails, which is not really a SQL query at all. But you could do more complicated things, like perhaps compute semantics. You could compute sentiment. You could compute all kinds of aggregations or different functionality. And I think an interesting question is, the bar is really, since you're supposed to be serving data, how much work do you want to offload for a particularly heavyweight CPU-intensive function? So that's something that you want to consider beyond the typical relational operations. Okay, so that about wraps it up. So the key design point here is that we want to retain the data semantics, and we want to make them available to the storage system in a way that it can interpret them. In our case, we're going to compute a subset of a table, and that way we have row-column partitions in the table. The objects know the table's schema, and that lets us do these operations. And then by scaling out and with these custom classes, we get the ability to utilize remote resources on the servers, which includes the execution classes as well as the local queryable metadata through that indexing mechanism. And that's about all I have. And I don't know if Carlos wants to mention anything more about our work with HDF5 and how that impacts or informs our work with Root, and as well for the work that you used to work. And that's all. Thank you.
Any questions?
You guys have any questions? Too fast. Sorry about that. Sorry for the rush.
No, we have plenty of time, actually. Yeah, one thing that we believe is that, and I think maybe Jim is going to talk about this a little bit, is that we can use the similar abstractions for other Access libraries as well. And we're actually now currently as Jeff already said, that we're experimenting with HD5. And I think that, working with the HD5 guys, labs, who are actually already working on hooking HD5 to object storage, and we're trying to solve some of their problems that they're running into with Skyhook abstractions. So I think that we can maybe also leverage that work for root data. If there are no other questions, then maybe Jim, you can maybe share your thoughts on how you think it could fit into IRIS-HEP work.
Yeah, I was wondering if there might be like a lot more questions after my talk. Questions to Jeff, actually, because at this point we're talking about SQL, and it's not clear how this will connect to physics work, but I'm sure that it can. So should I go ahead with my?
Yeah, go ahead.
I'll steal the share, and if I get unmuted, I'll unmute myself. Okay. So I guess I'm sharing, and I am not muted, so this is all good. All right. So here I'll be talking about how the project you just heard about fits squarely into what we want to do. So I've been trying to get a handle on all the different projects that are going on and how they all fit together. So this is my view of the world. It is not a coincidence that it is centered on me, because, make a graph starting from yourself until you don't know what's beyond the frontiers anymore. It'll look like that. So CROSS is most closely connected to DOMA, data organization, management, and access, naturally. But that also gets into things that we in the analysis systems are doing, because DOMA is so tightly connected to analysis systems. So within the analysis systems, one of the main themes is this n-tupeless future, where we have some sort of a query system so that physicists don't have to each individually download an entire copy of the data, like an n-tuple, a projection. We want to leave the big data up on some service and have the users be able to request reduced output. So we've talked about this quite a few times. And in the analysis systems, quite a few of us are working toward making this happen. So Mark and Ben are focusing on like the query scheduling aspect, using Spark quite a bit, data delivery, and the intelligent data delivery system, which I'll say more about later. Gordon, Emma, and Mason are focusing on a query expression language, and I have been focusing on event data processing with awkward array. Henry will be ramping up where his focus is on histogram aggregation. And so these are like three distinct parts of a query system that one would need. Also, we're not just working on this future thing, but with physics groups whose primary goal is getting physics results out. So there's these two CMS analyses from the CAFIA group at Fermilab, where they're using the awkward array event processing, and they are working with Ben, where Ben is developing distributed processing with Spark applications, and also Andrew Melo with his Spark cluster at Vanderbilt. So doing real physics on these things as we're figuring out how to work these systems. And one thing that's clear in this work is that it's useful to work with the analysis data as individual root branches converted to jagged arrays, rather than event records. And there are a variety of reasons for this, different reasons. Efficient processing in Python, analysis code readability. People, subjectively say that it is easier to read this way. But then what's important for this talk is the columnar granularity. that we get one column at a time instead of one event at a time. So the one-plot queries that I'm looking forward to, but it's not yet realistic, they would require some, less than 1% of the columns, but nearly all of the rows. So that's why this columnar granularity is on our mind. Now, whole analysis workflows, which are being demonstrated with COFIA, those two analyses, they both count up how many columns they've actually needed, and it's about 10%. And they are putting filters on rows, but they are loose. They're trigger cuts on rows. And then they do complex filtering afterward. So for applications like this, the unit of data is columns, not files or events. And so one of the DOMA projects is to create an intelligent data delivery system, or IDDS. The point of that is to respond to requests for data in high-level terms, like the muon kinematics columns in the first million events of 2018 data, rather than low-level terms like this byte to that byte of some file.root. The primary way we do it now is the latter, the low-level terms. That's what xroot-d does, from this byte to that byte. For query applications, we'd be requesting column segments, and maybe with simple cuts, like we might want to have the just something that passes certain trigger lines actually go over the network to the worker. But the complex filtering, the things that would be really hard to express, well, they would happen in the query system. That's not something that we believe can be pushed down, as Jeff described. So this is a good match to what we want from IDDS is a good match to what Skyhook can deliver. Format-aware data delivery, some reformatting at the source, I should say, like decompression, recompression, concatenation, slicing, and main thing, having intelligence close to the source. So you don't have to send a lot of data over the wire just to get rid of it. The difficulty here is that the root file format is complicated. So just if we want to translate a high-level query like muonpt in events 1 to 1,000, just finding those bytes is a non-trivial task. And one would need infrastructure like the root framework, or uproot, or groot, or root4j. But all of these are not simple programs. And so this places limits on how close to the storage intelligence can go. Like if we're talking about some kind of small embedded device, it could be hard to get any one of these systems onto it. However, each of the local entities, like muonpt, events 1 to 1,000, it does have fixed byte ranges in the files, as long as these files are not changing. So a full framework can identify the ranges and save those ranges to an index to simplify lookups. So you heard Jeff talk a lot about indexes. This is what we should be able to index root files. So to start in this direction, I made a very small project. If you go to that repo, you'll see that there's not a whole lot there. It uses uproot to map logical row and entry numbers and column names to the low-level T-basket locations in the root files. This index is formatted as flat buffers, which Jeff is using elsewhere in the Skyhook project. So any process that can read flat buffers can deliver jagged arrays from the indexed root files. So just to show a bit about what this looks like, this is actually the entire flat buffer schema. Just what's the file name, what are the names of the columns, i.e. branches, where are the baskets located, with a little bit of complexity because baskets can consist of several compressed pages. But this completely describes how you get from high-level view to a low-level view. So current status, and I didn't see Jeff's talk before writing this. So what Skyhook provides is a good match to what EdDDS is trying to achieve. The unit of data for a query system is a column segment. So I provided Jeff with a way to generate mappings from high-level entities to low-level byte positions, so that we'll be able to have an index like that. And it would be very interesting to see how this can be used, either to organize how objects are distributed, or putting intelligence close to the storage that knows how to deliver arrays instead of baskets. All of that would be interesting, so I'm just like to see how that's going.
Thank you, Jim. This is awesome. So what would you, so after you've seen Jeff talk today, you said already that that one of the things that Jeff focused on databases mostly. That's basically the main goal of the project, as at least initially was conceived, right? And so, is there anything else that you were surprised by, or that you thought that was missing, or anything that that you would have liked to see in that talk?
No, it looks like all of the components, like even though it is database focused, I think there would be nothing stopping from doing the same sort of thing on collections of root files. Like the kinds of operations we want to do are fewer. Like I don't foresee any very complex selecting or projecting on the, and certainly not aggregation on the storage layer. But the business of taking bytes, interpreting them as arrays, and then actually like slicing the arrays. Like I don't want to get back 1,000 little baskets. I want to get back one big array. The concatenation, decompression, recompression, please send it to me in a less compressed format than LZMA. All of these they sound like they're within the range of the kinds of operations you've been doing.
Thanks. Jeff, any reactions? Are you still there?
Okay. Hello?
Yeah.
Okay, good, yeah. Yeah, I agree. That definitely sounds. And that's indeed.
Are there any questions now from the audience questions on Jeff's talk now that we see how it connects? Did we lose everybody with the technical problems at the beginning?
I'm not sure.
I'll ask a simple question.
Okay.
When do we get to try it?
That's a very good question. Yeah. I think that I think Jeff can talk more about it, but I think that we want to sort of like go in stages, and I think that the first step that Jim suggested, like where we can get sort of the earliest possible exposure to Coffea, would be a really good step. And I think we're right now mostly looking at sort of our inter-object the restructure of objects within, of objects inside of objects. But I think that maybe just to get a sort of a demonstration going, it would be good to just hook it up to Coffea as the fastest way, in the fastest path possible, and then maybe foregoing some of the operations that we're envisioning, and just see what happens, right? And see how we can maybe use this as a baseline, and what kind of things we encounter in order to see whether this works.
Sounds good.
So Jeff, do you have also some particular feedback on suggestion that Jim suggested as a path to get Skyhook hooked up to Coffea? I mean, what do we need to do to get that done?
Yeah, that's hello.
Yeah.
Yep, we hear you now.
And I keep losing my. I'm sorry. The question was the status. That's still in progress.
No. Basically, so Jim, in his talk right now, he just sort of created, showed a path, and we discussed that before.
Oh, right. Yeah. Yes.
So what we need to do to actually, because I think that's actually, it's a very valid, it might be actually the best way to really understand how Skyhook could help here, is to just get it into a state where it can be used in Coffea, and then we can, it's sort of like the open source way, right? Release early and release often. And so this might actually then very quickly get us to a point where we can actually see what helps and what doesn't help. And I'm wondering, what we need to do in order to actually hook Skyhook up to Jeff's Jeff's hook that he built, or Jeff's, I don't know what I would call it. It's a stub or something, right? Sorry, that Jim's stub, that we can work with Jim's stub that he built for us.
Sounds like just need some sort of containers or some sort of server implementation that has the subcluster and this schema that Jim's created, and presumably just a small little interface stub that you can request certain columns, and from there I think we could glue onto that. And then as for data, well, there's some 20 gigabytes of open data now available thanks to the root theme. We can just try with that.
Mm-hmm.
Seems doable. Just have to pick a site and a deployment mechanism.
Right. Yeah, actually, that's a really good question, right? Do we have? It's probably best to, since you have already the whole Coffea stack in place somewhere, right? Is there like room for actually installing?
It's pip installable. It just lives on top of NumPy.
Well, maybe more the question is where. So there's a lot of work at Vanderbilt with Andrew's cluster. I mean, that's where most of the Coffea work is going on right now, is my understanding.
Okay.
They're in LPC Condor, but obviously the former has a bit more flexibility with regards to new installations.
Mm-hmm. Right.
And he is not here, so he can volunteer.
Exactly, yeah. That's Spark-based. Do you think that we could have a Normally, Spark likes to control the data layer, and here we're talking about an alternative.
I
I
suspect
don't know
we'll
if
have
that's
to
gonna be a
start
problem.
simpler, right?
Yeah.
I think it'll be, you know, like sockets and stuff.
Or maybe that parcel that Lindsay got working like yesterday. Well, we're brainstorming in the meeting right now.
Yeah, I should probably take this offline.
Yeah, let's just do that. Okay, so good. Jeff, any reactions, or are you having difficulties with the audio again? Sounds like it.
Okay. Okay.
Yeah, I think that's well, we're out of time almost. So, well, thank you, and then maybe Jim and Nick, we can take it offline and then discuss how we can actually deploy a Skyhook cluster, and just try to hook it up and see what happens.
Right. Okay. Yeah.
Excellent. Thank you so much.